Let us solve another question on pipelining, which was given in the year 2013 for 2 marks. Let us see how does it go. Consider an instruction pipeline with 5 stages without any branch prediction. Fetch instruction, decode the instruction, fetch the operand, execute the instruction, and write operand. The stage delays for FI, DI, FO, EI, and WO stages are 5, 7, 10, 8, and 6 respectively. Okay, so these are in nanoseconds. There are intermediate storage buffers after each stage, and the delay of each buffer is 1 nanosecond. A program consisting of 12 instructions, that is I1 to I12, is executed in this pipeline processor. Instruction I4 is the only branch instruction, and its branch target is I9. If the branch is taken during the execution of this program, the time needed to complete this program is 132, 165, 176, 328. Okay, let us get into the details first of all. First, we understand what are the details provided, what is the data that is actually provided to solve this question. Eventually, the question is the time needed to complete the program is. Okay, we need to find out the time. Okay, see, that is the time to execute. This is what we need to identify and find out. Okay, as this is a pipeline processor, we need to calculate pipeline time, right? The pipeline time. We need to calculate pipeline time. Okay, pipeline time generally is calculated by using a formula k plus n minus 1 into TP, right? Yes, generally we are going to calculate the time of a pipeline for executing n number of instructions by using k plus n minus 1 into TP, in which k is the number of segments, n is the number of instructions, minus 1, TP is pipeline time, that is maximum stage delay maximum stage delay plus maximum register delay. So, of course, we can solve by using this, but because there is a hazard, if you can look at a program consisting of 12 instructions I1 to I12 is executed in this pipeline. Instruction I4 is a branch instruction, so that there is a branch hazard. Okay, since there is a branch hazard, finding the time to execute in the pipeline may be somewhat complex by using this method, but still we are going to find out the time that is going to be taken in the pipeline for executing the same program still by using this. But we need to have some additional steps required because there is a branch. So what we can do is, the pipeline time can also be understood, can also be identified by using another method, which is called space-time diagram. By using space-time diagram, it will be simpler. The space-time diagram, it will be simpler. Now, I'm going to explain you both methods. That is, we're going to find out the pipeline time by using this formula as well as the space-time diagram. Now we'll examine the space-time diagram, after which I'm going to explain you by using k plus n minus 1 into TP formula. Okay, let us understand the details that are provided. The total number of instructions are 12. That is, I will write it here: I1, I2, I3, I4, and I5, I6, I7, I8, and I9, I10, I11, and I12. There are altogether 12 instructions, right? Here it is given that this is I4 is the branch instruction and the branch is taken and the branch target is I9. That is, I4 is the branch instruction and the branch is taken, the target is I9. That means that when I4 instruction gets executed, the branch will direct the control to I9 directly. That means that I5, I6, I7, I8 will not be executed in this. Okay, the branch instruction is I4. This branch will take you to I9. Branch target is I9. So the number of instructions that will get executed in the program is just 8 instruction. That is I1, I2, I3, I4, and I4 will directly branch to I9, I9, I10, I11, and I12. Okay, this is the program that is needed to be executed. A total of 8 instructions, right? Number of instructions, I will write it here. Instructions are equal to I1, I2, and I8. Total number will be I8. But last 4 instructions will be I9, I10, I11, I12. Collectively, there are a total of 8 instructions that are going to get executed. Because these instructions are not getting executed since the branch is taken branch. I4 will direct you to I9. The total number of instruction will be just 8. I1, I2, I3, I4, I9, I10, I11, I12. In order to make it clear. Okay. Now, let us calculate the time TP. Okay. What is TP? TP is the time, the clock cycles that are required to execute one task. TP is the clock cycles that are required to execute one task, which is equal to max stage delay plus max register delay. Okay. So here it is given in nanoseconds. Max stage delay is 10 nanoseconds. Max register delay is 1 nanosecond, right? So the number of nanoseconds that are required in the pipeline to execute one task, one instruction is 11 nanoseconds. Okay. So one clock cycle is equal to for this pipeline, it will be 11 nanoseconds. Okay. Keep it aside. Okay. And when you look at this, there are intermediate storage buffers that are, of course, it is given a program consisting of I2 12 instructions, I1 to I12 is executed in this pipeline processor. And if the branch is taken during, this is what we learned. And just I'm seeking for an additional detail. Are we provided with any branch prediction? Okay. Without any branch prediction here. Okay. Here, in order to handle the control hazards, there are no provisions in this pipeline. Okay. So that means that when I4 instruction is getting executed, we need to wait to get the next instruction into the pipeline till I4 instruction gets completely executed. Okay. So let us see. So what we do is we are going to draw a space-time diagram. That is, it looks this way. In the space-time diagram, on the x-axis, you're going to have the clock cycles. These are the clock cycles. Okay. We are going to plot the clock cycles T1, T2, T3, T4, T5, T6, T7, T8, T9, T10, T11, T12 to T15. If there are more number of clock cycles required for executing this instruction, the x-axis length will be more because T16, T17, T18 will also be following. Okay. But since we just require only 15 clock cycles, as in this case, we just used the number of clock cycles which are equal to 15. Why we have come to a conclusion that only 15 clock cycles are needed to execute all these instructions? We are going to see this. Unless we see this, we can't understand why we're going to take 15 clock cycles for executing this. Okay. Now let us see. When the instruction I1 gets executed, it is going to enter into fetch in T1. Then it enters into decode in T2, fetch the operand in T3, execute the instruction in T4, and write the operand. This is T5. Okay, you clear see here? These are the stages. Those are fetch the instruction, decode the instruction, fetch the operand, execute the instruction, and write operand. These are the stages. Every instruction should have to enter into these stages. I1, in the first clock cycle, it enters into the first stage, which is fetch the instruction. I1, in the second clock cycle, it enters into the decode stage. In the third clock cycle, it leaves the decode stage and it enters into fetch the operand stage. In the fourth clock cycle, it leaves the fetch operand stage and it enters into execution stage. In the fifth clock cycle, it is going to leave execution stage and enters into write the operand. Now I2 will be entering into the fetch the instruction stage in T2, because in T1 it is occupied. I1 occupies fetch the instruction stage. So the moment I1 enters into T2, I2 enters into the fetch stage. So it will continue. That means that in T6, I2 gets finished. In T5, I1 will get finished. In T2, I2 gets finished. So I3 enters into the pipeline in the third clock cycle, because in the second clock cycle, the fetch the instruction stage is occupied. So it needs to wait for the fetch the instruction stage to be available. Okay, it is available in the third clock cycle. So it keeps on entering after I2. Okay, so finally it finishes its execution at the T7th clock cycle. Similarly, I4 enters into the fetch the instruction stage in the fourth clock cycle. It leaves the pipeline in the 8th clock cycle. But T4 is a branch instruction. Okay, as it is a branch instruction, the branch condition needs to be evaluated. The branch condition needs to be evaluated. Unless the condition gets evaluated, next instruction cannot be fetched. When the condition will get evaluated, the condition will only get evaluated in execution stage. Right? The condition will only get evaluated in the execution stage. Right? So, till the execution stage, next instruction cannot enter into the pipeline. Okay, till the execution stage finishes, next instruction I9 cannot enter into the pipe. So I9 can enter into only 8th clock cycle. Okay, because in the 8th clock cycle, execution stage of I4 has been finished. After execution, that means that ALU operation is finished, right? Okay, if the ALU operation is finished, then the condition finishes. Condition will get evaluated. We need to wait only till condition gets evaluated. We need not wait till write back stage. This write back stage is simply a write back to the memory. Okay, so some results will get transferred back to the memory. We need not wait because it doesn't occupy the write back stage, doesn't require ALU. Okay, so till what time, how much time we need to wait? The next instruction needs to wait. Next instruction needs to wait till execution stage finishes. After the execution stage, ALU computes the condition. The condition will be evaluated to either true or false. Okay, so definitely we are going to identify what is the next instruction. In this case, the condition evaluated to true, let us say, as in the question, and I9 is the target instruction. Why we are assuming that condition is evaluated to true? Because when the condition is true, then only branch will be taken. If the condition is false, then subsequent instruction will be taken. So here I9 is the branch instruction that is taken. So the condition is evaluated at the EI stage, that is the execution stage. After EI, I can enter into the pipe, that is 9th instruction can enter into the pipe in 8th clock cycle itself. Meanwhile, in the 8th clock cycle, I4 is writing the result back to the main memory. I need not wait for this. Just a short while ago, I told you why I don't need to wait for the I4 instruction to write the result back to the memory, because simply it is writing the result back to the memory. Branch target address will be computed in the execution stage itself. After the execution stage, definitely we know what is the target address, and next instruction which is at the target address is going to enter into the pipeline in the 8th clock cycle itself. Okay, and it goes this way. I9 will be in the T8th clock cycle, it is in fetch the instruction stage. In T9, that is 9th clock cycle, it is in the decode the instruction phase. In the 10th clock cycle, it will be in the fetch the operand stage. 11th clock cycle, execute the instruction. 12th clock cycle, write back. So obviously, subsequently, I10 will enter into the fetch the instruction stage in the 9th clock cycle. Similarly, it is going to finish in 13th clock cycle. So I11 is going to finish it in 14th clock cycle. I12 is going to finish it in 15th clock cycle. Right? So the number of clock cycles that are required, number of clock cycles that are required is equal to 15 into each clock cycle. What is the clock cycle time for a pipeline? Clock cycle time, you know that? Clock cycle time is equal to TP, which is equal to max stage delay plus max register delay in the pipeline. Pipeline time, clock cycle time, T is equal to TP is equal to max stage delay plus max register delay. So max stage delay is equal to 11, max register delay is equal to 1, total is equal to, sorry, it is 12. Excuse me, let me, 10 plus 1, sorry, 11 only. Okay, I was correct in the earlier scenario. Total is 11. So number of clock cycles is equal to the total number of clock cycles that are required to complete the program, which were equal to 15 into 1 clock cycle time. Clock cycle time is equal to 11 nanoseconds. 15 into 11 is equal to 165. This is the correct answer. Okay, 165 is the correct answer. B is the correct answer. Now, a simplest method, if you can actually understand, we'll use the same formula. We'll use the same formula, that is K plus N minus 1 into TP, right? Pipeline time is equal to K plus N minus 1 into TP. Already we got the answer. Okay, the people who just want to solve the question by using space-time diagram, of course, you got the answer, but from my side, I'm giving you another way of solving this. If you can actually understand the question, we can solve it another way by using this K plus N minus 1 into TP. Okay, what is K? But here, of course, K is equal to, anytime the K is equal to, how many the stages, how many number of stages? 1, 2, 3, 4, 5 stages. You know that the K is equal to number of stages. Number of stages are equal to 5. Here, the number of tasks, hold on, number of tasks will be 8, but actually we need to calculate for the first 4 and the next 4 separately. 5 plus 4 minus 1 into TP. Okay, that is because these are divided into 2 different kinds of sets. That is, after executing the first set, the next set will be getting executed, right? So what we do is separately we'll execute 5 plus 4 minus 1 into TP. That is equal to 8 into clock cycle time, 11. Okay, 8 into 11 is equal to 88. Okay, so 88 nanoseconds are needed for the first 4 instructions. Next 4 instructions also same thing, because next 4 instructions also 5 plus 4 minus 1 into TP is equal to 88, because number of segments will be 5, number of instructions will be 4, minus 1 into TP is equal to 8 into 11 is equal to 88. So what we do is we add both. 88 plus 88 is equal to 176, right? But hold on, there is a mismatch. This is 165, this is 176. Because here we need to subtract an overlapped clock cycle. We need to subtract an overlapped clock cycle. The total number of clock cycles are equal to 8 plus 8, right? These are the clock cycles that are required for the first 4 instructions, and these are the clock cycles that are required to execute the next 4 instructions. So the total number of clock cycles will be equal to 16. Okay, but 16 minus 1 will be equal to 15. Go back. Here, there is an overlapped clock cycle, right? Okay, that means that if this instruction starts from I9, then there won't be any overlap. But since the 9th instruction will get started from the 8th clock cycle itself, since for the write back stage we don't need to wait, there is an overlapped clock cycle. So the total number of clock cycles that are required by the first 4 instruction is equal to 8, but the next and also next for the next instruction also is equal to 8, but there is a overlapped clock cycle. Okay, this overlapped clock cycle must be subtracted. Okay, that is 8 plus 8 minus 1. Number of clock cycles are equal to 8 plus 8 minus 1, that is equal to 15. 15 into 11 is equal to 165. Okay, so 176 minus 1 clock cycle time. 176 minus 11 is equal to 165, because 176 is the number of nanoseconds for 16 clock cycles. But we need to subtract 1 clock cycle time, that is 11. 11, that is equal to 165. This is the answer. Okay, but whenever you just get these kind of questions, always try to solve by using space-time diagram, which gets simpler. Okay, that's the answer. 165 is the answer. Answer is B.